Hello, this is MAT221, Calculus 1. This is Mrs. Johnson. This is section 4.8, which talks about antiderivatives. So we were talking about the general antiderivative. So I want you to now think backwards now to think, okay, if we know all our 26 derivative rules, we should be able to go backwards for some general, relatively easy functions. For instance, if I knew that the derivative function was sine of x, what would be the function whose derivative is sine of x? Well, if we think about this, the derivative of cosine is equal to negative sine of x, which means the derivative of negative cosine of x must equal sine of x. So the antiderivative of sine of x is negative cosine of x plus c. Remember, the general antiderivative always includes a possible constant, because if I take the derivative of this function, I should get back to the original derivative function that I was given. So if I take the derivative of the antiderivative, I should get back to this function. And remember, there's always possibly a constant that would possibly be attached that when I took the derivative would disappear. What about part B? What would be the general antiderivative of 1 over x? Now, this should look familiar for one of our derivative rules. We know that the derivative of the natural log of x is 1 over x. So we know the general antiderivative of this function must be the natural log of x plus c. Now, what about part C? When we use the power rule, remember when we went backwards from x squared, we said, well, that's equal to 1/3 x to the third plus c, because when I take the derivative of this, I get x squared. If I said the derivative function was x cubed, then that must have come from x to the fourth, but there's no coefficient in front. So I must have had a 1/4 coefficient to make it disappear. So when I take the derivative of this function, I get x to the third. So here's my general antiderivative rule for power functions, or the power rule backwards. And we'll do more of these in the next video also. It says that the antiderivative, the general antiderivative of any function x to the n is equal to x to the n plus 1 over n plus 1 plus c. So before I leave this particular PowerPoint, I want to talk about something called rectilinear motion. This is done mostly in physics. It is when a particle is moving along or an object is moving along a straight line. It is called rectilinear motion. Anti-differentiation is particularly useful in analyzing the motion of an object moving in a straight line. And recall that if the object has a position s, which is f of t, and then the velocity is going to be the derivative of that function, or s prime of t. This means that the position function is the antiderivative of the velocity function. Likewise, the acceleration function, a of t, is the derivative of the velocity function. So the velocity function is the antiderivative of the acceleration function. So if the acceleration and initial values of s of 0 and v of 0 are known, then we can actually find the position function by taking the antiderivative twice. So let me give you a couple of examples here. If I said to you, a particle moves in a straight line and has an acceleration given by a of t equals 6t plus 4. You know that its initial velocity, that is v of 0, is equal to negative 6 centimeters per second. And you also know that its initial displacement, its position, at time equals 0 is equal to 9 centimeters. Find the one and only one position function where this will be true, that the acceleration would be this given equation, and these two initial conditions would also be true. So what we do here with rectilinear motion problems is we take the acceleration and we go backwards, and we take the antiderivative of acceleration, which will bring us to velocity function. The velocity function would be the antiderivative of this function. Now, using the rules we just had here, if I have 6, this is just a constant that I can move to the front. The antiderivative of t would be t squared over 2. The antiderivative of 4, this is actually, if I have just a number, that must have been 4 times t, plus perhaps a constant. So I'm going backwards, taking my antiderivative. Now, we could always check to make sure we've done this right by taking the derivative of this function. 2 goes into 6 3 times. The derivative of 3t squared is 6t. The derivative of 4t is equal to 4. And the derivative of the constant would be 0. So we can see that the derivative of this function would bring us back to the acceleration function, which was given to us. Now, we also know that the velocity at 0 equals -6, which gives us an initial value problem where we can actually solve for the value of c by putting 0 in for t and -6 in for the velocity. When I do that, I get -6 as my, I get -6 as my constant. So when I put 0 in for my t and -6 in for my velocity, I get my constant is equal to -6. So my velocity equation becomes this equation. Now let's take the antiderivative again. What would be the antiderivative of 3t squared? Well, that would be t to the third. Because when I take the derivative, it would be 3t squared. The antiderivative of 4t would be 4 times t squared over 2, or 2t squared. The antiderivative of -6 would be -6t, plus perhaps a constant. Now, the book uses d, but I usually just use another c value there, right? So here's my antiderivative function, and let's just simplify it a little bit. There's my antiderivative function of velocity. And when I take the antiderivative of velocity, I go to position because I'm going backwards in my derivatives here. But it was given in the last slide, right? We are given that s of 0 equals 9. So when t is equal to 0, which makes all of these values 0, d would equal 9. So that would be our position function. S of t would equal t cubed plus 2t squared minus t to the 6t plus 9. So we now have the position curve that has an acceleration of 6t plus 4 and has those initial conditions of the velocity at 0 equals -6 and the position at 0 is equal to 9. Now I just want to give you a little bit of a heads up here. We don't always have it so that the initial condition ends up being the value of c or d. It just happened in this case because we had a polynomial and we were putting in 0 in for t, but that doesn't always happen. So let me give you another example of rectilinear motion here. Find the velocity and the position equations for a downward acceleration of 9.8 meters per second squared and an initial velocity of 1 meter per second downward and an initial position at 0, 0. Well, we can definitely know this from physics. This is negative 9.8 meters per second squared is the acceleration due to gravity. So if we're given the acceleration due to gravity, and let's let downward be positive in this case, although we could put a negative value in there, the antiderivative of this would be the velocity. So the antiderivative of 9.8 would be 9.8 t plus c. But we're given that the initial velocity at time equals 0, initial velocity, is equal to 1 meter per second. So I know that the velocity will be 1 when the time is 0, so the c value here would be 1. So my velocity equation would be 9.8t plus 1. They asked me for the position function, so I have to go backwards once again. So let's go backwards once again. Since velocity is the derivative of position, we have to take the antiderivative of velocity. This would be the 9.8 comes to the front. I'd get t squared over 2 plus the antiderivative of 1 is just t, because we know the derivative of t is 1, plus again, possibly some constant. But again, here our constant is 0, 0. So putting in 0 for my position and 0 for my time, in this case, my constant is 0. So my position equation is equal to 4.9 t squared plus t. I found my initial position function given the acceleration due to gravity and a little bit of information about the object. Here's my acceleration, there's my velocity, and there's my position. So I'm going to put up another video too going backwards with some other of these rules going backwards, but here are some basics we have for rectilinear motion, and we have some basics for the original going backwards for the original derivative curves that we had. I also have a worksheet in the worksheet folders, worksheet 4.8, which actually talks more about this concept of the formulas for going backwards for antiderivatives. Have a good day.